So before we get to induction, I have a very simple question for you. What's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10? That is, what's the sum of all positive integers from 1 to 10? What if I asked you to add the sum of all positive integers from 1 to 100? Would you know that it's 5050? I can make this problem easier for you no matter how big that last number gets. Now, a quick disclaimer, this is not a proof right here. A formal proof comes later, but here's just a fun little trick. Let's look at the sum of all positive integers from 1 to 100. Let's look at the numbers from the very outside. What's 1 plus 100? 101, of course. Now, move inward on both sides. What's 2 plus 99? 101 again. What's 3 plus 98? Again, 101. In fact, this sum is just the sum of a bunch of 101s. The question is, how many 101s? Well, each mini-sum uses two numbers, and from 1 to 100 there are 100 numbers. So it would use half as many numbers as the number of numbers, or 50. So if this sum is just 50 101s, doesn't that just mean that it's 50 times 101? And that's 5050. Ta-da! And you can do that with the other sums too. So it would seem like the sum of all integers from 1 to n is n times n plus 1, all divided by 2. What if we wanted to prove what we think might be true? What if we wanted to prove that the sum of all positive integers from 1 to n is equal to n times n plus 1, all divided by 2? Well, there's many ways to prove various statements, but the way that's the easiest in this case is induction. So let's make some terminology here to make our proof both rigorous and easy to understand. Let's define the statement as the sum of all positive integers from 1 to n is n times n plus 1 divided by 2. Our goal is to prove the statement true. You see, the statement is very hard to prove in isolation. So what if we instead chopped up the statement into every one of its cases? What if we solve the statement for n equals 1, then we solve the statement for n equals 2, then for n equals 3, then for n equals 4, then for, okay, this might take a while. How about instead we split up the statement into just two parts? First, we prove the statement true for the simplest or the first situation where n is equal to 1. This is known as the base case. Then, and stay with me here, because this next sentence is going to be a doozy, we want to prove that if the statement is true for any arbitrary n, then the statement is true for the next case in the sequence n plus 1. This is known as the inductive step. So, let's break that down. Does proving those two facets prove the statement to be true? Well, if the statement is true when n is equal to 1, and it is the case that the statement is true for the next in the sequence given that it's true for the previous, then suddenly the statement is true for every case. That's just the logic for the inductive reasoning. Now let's do the actual formal proof. In order to prove the statement, we want to prove that the statement is true for n equals 1, then we want to prove that if the statement is true for n, then the statement is true for m equals n plus 1. Let's do the base case first. Let n equal 1. 1 is equal to 1 times 1 plus 1, all divided by 2, so 1 is equal to 2 divided by 2, so 1 is equal to 1. We've proven the base case that the statement is true for n equals 1. Now let's prove that if the statement is true for n, then the statement is true for m equals n plus 1. Here's where the logic can get a little muddy for some people. We're trying to prove an if-then statement, so we actually can safely assume the if part. We just need to prove the then part, provided the if is true. So we assume the statement is true for n. That is, 1 plus 2 plus so on and so forth plus n is equal to n times n plus 1, all divided by 2. Now we want to prove the statement true for n plus 1, which we'll call m. Since we assumed that the statement is true for n, we have that all we did here was add n plus 1 to both sides of a true statement, which is still a true statement. Our goal here is to show that what we have on the right side of the equation here is equivalent to the situation where the sum of all integers from 1 to n has n replaced with n plus 1, which is this, n plus 1 times n plus 2, all divided by 2. The rest is just algebra, and here it is. Oh, look at that. That's what we were trying to prove. Done. So yes, we just proved that the sum of all positive integers from 1 to n is n times n plus 1 divided by 2. Congratulations!